Alright, in section 10.5, we're talking about the polar form of complex numbers. So first off, what a complex number is, it looks like this form right here, a plus bi. So this first part is actually what we call the real part, and the second part is what we call the imaginary part. So the real part of the number, a, and the imaginary of the part of the number, bi. Okay. Now, what we're going to use these for is using complex numbers. If you change them to a polar form, then it's actually going to make the calculations just a little bit easier to work with. Okay, so now this is not your x-axis anymore. It's called the real axis. This is not the y-axis anymore. It is the imaginary axis. Now, say we were going to plot this complex number to negative 3i. Well, there's your real part, there's your imaginary part. In order to plot it, it's basically the same thing as plotting 2, negative 3. So you would go over 1, 2, and then go down 1, 2, 3. So that'd give you that point right there, and that's it. Now, something called the absolute value of a complex number. So if you have this complex number, and now I just changed the a to an x and the b to a y, but it still has the same form, so that's a complex number. To find the absolute value of that, so the absolute value of this complex number z is the square root of both parts, the real and the imaginary part, and then you just add them together. Now, what that means in general, it's the distance from the origin to that point xy. Now notice this is also called the modulus of a complex number. So the absolute value of a complex number and the modulus of the complex number are the exact same thing. Okay, so if we just took a random point xy, and here's a complex number x plus I or yi, so the distance from the origin to that point, that is the absolute value or the modulus of your complex number. So that distance right there. Okay, if they give us this square root of 5 minus I and they say, okay, we'll find the absolute value. Well, we need to use the square root of x squared plus y squared. Here our x is the square root of 5 and our y is negative 1. That number right in front of I. So the absolute value of this complex number, the square root of 5 minus I, is equal to the square root of the square root of 5, that thing squared, plus negative 1 squared, which the square root, if you square a square root, it's like these cancel out and you're just left with 5, plus negative 1 times a negative 1, that would just give us 1. Okay, so that would be the square root of 6. Okay, so that's the modulus or the absolute value of this particular complex number. Now this represents the distance from the origin to this point right here. And this point can be described as the square root of 5, comma, negative 1. Okay, so this is what it would look like. There's your point right there. The square root of 5, comma, negative 1. The distance from the origin to that point is the square root of 6. Okay, if we do the same thing for this complex number, we're going to have z, absolute value of z, which we're saying z is a complex number, is the square root of x squared plus y squared. Our x is 3 and our y is negative 4. So the absolute value of this complex number, 3 minus 4i, is equal to the square root of 3 squared plus negative 4 squared, which that would be 9 plus 16, or the square root of 25, which that would be 5. Okay, so there's our absolute value, or the modulus of our complex number. So from this point, which we can describe it as 3, negative 4 on the complex plane, from the origin to this point right here, 3, negative 4, this has a distance of 5. Okay, now if we want to write the complex numbers in polar form, if you notice the absolute value of our complex number z, the formula for it is the exact same one for the radius that we've been using. So if we take this right here, if we find cosine of theta, which is x over r, then we can solve for x. That would be r cosine theta. Do the same thing for sine of theta, which is y over r. Solve for y, that would be r sine of theta. Now notice our r is not called the radius anymore, it's called the modulus, the distance from the origin to this point. And our theta is not called a theta anymore, it is now called the argument. But it's really essentially talking about the same thing. Okay, so this is the information we need right here. Okay, so if we're going to go from a polar form to a complex number, I need x is equal to r cosine theta, y is equal to r sine theta, and r is equal to the square root of x squared plus y squared. Okay, so if you look at our complex number, x plus yi, then to transform that into a polar form, well, we just said x is r cosine theta, so I'm going to change this x to r cosine theta. Y is r sine theta, so I'm going to change this y to r sine theta and then tag the y, or the I, right there in front of it. Since both of them have an r, I can factor that out. So the polar form would be r times this whole thing, cosine theta, plus I sine of theta. Okay, where here r is the modulus and theta is called the argument. If you wanted to write the shorthand of this right here, that would be it right there. Those two things are the exact same thing. Now make sure that theta is in standard position with the terminal side containing this point. The most important thing is make sure your final angle is in standard position. Okay, so write the complex number 4i in polar form. Now it says on the complex plane the number z equals 4i, that's the same thing as z is equal to 0 plus 4i. So our real part is 0 and our imaginary part is 4. So the first thing that we need to find is r, which is the square root of x squared plus y squared. So our x is 0 and our y is 4. So r is going to be 0 squared plus 4 squared, which that's going to be the square root of 16, which r is just going to be 4. The next thing that we need to find is our theta, or we call it our argument. We can use x is equal to r cosine theta. Where we said x was 0, we just found r to be 4 cosine theta. If I divide both sides by 4, so 4 over 4 gives me cosine of theta. Well, then this is really just 0, and I'm going to switch these. So cosine of theta is just 0. Okay, well, I'm not looking for cosine theta, I'm just looking for theta. So I can use the inverse of cosine of 0, or what we can really use is the unit circle. Where is cosine 0? Well, at this point, it's 1, 0. Cosine represents the first number. Here it's 0, 1. Cosine represents the first number. So right there. So that is 90 degrees. So theta is 90 degrees. Okay? So then I need to put it back into this form right here. Oops. This form right here. Okay? So I'll have R is equal to 4, then cosine 90, plus I sine 90. Okay, now this right here is the trig form of 4i, and that'd be your final answer for that one. Okay, we're going to do the same thing. Write the complex number 3 minus 2i in polar form. So first we need to find our r, which is x squared plus y squared. Our x is 3, our y is negative 2. So r is the square root of 3 squared plus negative 2 squared, which that would be 9 plus 4, or the square root of 13. Then we need to find our theta, or the argument. We can use x is equal to r cosine theta. So x is 3. We just found r to be the square root of 13. Cosine theta. Divide both sides by that square root of 13. Okay, so cosine of theta is equal to 3 over the square root of 13. I need to find just the argument, so I'm going to move cosine over to get the inverse cosine of 3 over the square root of 13, which my calculator will give me 33.7 degrees. Okay. Now before you say, okay, that's my answer right there, we need to figure out what quadrant is that in, because this is the same thing as plotting 3, negative 2. Okay, so if we go over 1, 2, 3, 1, 2, we're going to be in the fourth quadrant. Okay, 33.7 is not an angle that's in the third quadrant, or the fourth quadrant. Okay, so really, what our calculator gave us was 33.7 degrees for this little angle right here. What we need is this angle in standard position. So what I need to do is 360 minus 33.7, which will give me 326.3. Now the reason that your calculator gave you 33.7 is because we used the inverse of cosine. And remember, that's only going to give you angles in quadrant 1 or quadrant 2. So this is where we had to be smarter than our calculator. So we need to use the 326.3 degrees for our angle and not the 33.7. Okay, so our polar form of this complex number would be, see how to write the other one. Actually, this should be a z. Since we're saying z is a complex number. Okay, so z is equal to our r, which is the square root of 13, or the modulus, cosine of 326.3 plus I sine of that same number, 326.3 degrees. And this right here would be the polar form of this complex number.